Thank you both so much. I really appreciate the invitation to be here today, and thank you also for the very kind introduction. The theme of today's symposium is two things that are near and dear to my heart, so very much at the crossroads, one of which is circular economies, sustainability, the other is metal sulfide catalyst. So that's definitely the theme that we'll be diving into today. I realize that we have a very broad and diverse set of researchers in the audience today, and congratulations on us scoring the best room in the house. I want to lead you through this, pedagogically take you on a journey on kind of the origins of where transition metal sulfide catalysts have really played a big role in developing new hydrogen technologies. So that's the big theme for today. And I'd like to start really where I typically do, and that is a recognition of what I consider to be one of the greatest achievements of humankind, and that is the modern fuels and chemicals industry as we know it. If you take a look at the processes on the screen, the molecules that we're creating with those processes, hydrogen, ammonia, gasoline, plastics, take a look at the scales on the order of 100 or hundreds of billions of kilograms a year, produced across the globe, shipped across the globe, used across the globe, providing a high quality of life for billions of people on Earth. It's really a truly magnificent system that we've developed. However, we know it's imperfect, and there are new driving forces that exist today that didn't exist when these were developed. For instance, sustainability and a circular process, as well as equity. So while these processes absolutely benefit the lives of all of us in the room here today, everybody in Lyon, in Europe, in North America, it accesses billions of people. It does not access all billions of people equally. So the question is, how can we make these molecules that are so important to us and make them in a sustainable, circular manner? And so here is a moment where I get to appreciate my team that I get to work with every single day at Stanford and at SLAC National Accelerator Lab. I serve as the director of a center called SunCat, and we're the Center for Interface Science and Catalysis, so we're all about chemical transformations for energy and sustainability. And we're really a team of researchers by partnering with a national lab and a university ecosystem, leverage a lot of tools, capabilities, and expertise to approach these big challenges in chemical transformations. Now, hydrogen is going to be the theme of what I want to speak to today, and as you saw from one of the earlier slides, the scales of hydrogen production are massive. It's approaching 100 megatons a year, and that's because it's an absolute cornerstone molecule in our modern society. It's used for so many different reasons, including hydrotreating operations in oil refineries, ammonia synthesis for fertilizer production, amongst many, many, many others. And the big question is, how can this grow potentially? If we can make hydrogen sustainably, and it is not currently made sustainably, it is mostly made, of course, from fossil fuels, and steam methane reforming is the #1 process to produce that hydrogen, which produces a stoichiometric amount of CO2. How can we develop new processes to make them sustainable, make hydrogen sustainably, and then use it not only for the applications that we already require today, but for other applications ahead? And one of the big questions here is, well, how are you going to make it renewably? And naturally, we have to use some form of renewable energy, and solar energy is a very natural one. There are many other sources of energy that we can use, geothermal, we can use nuclear, we can use many other sources of CO2-free energy. But what I want to focus on today is really coupling solar technologies with hydrogen evolution catalysts to see if we can drive water electrolysis to make hydrogen in that manner. This was a thought that has been around for a very long time, frankly, but it really wasn't until the last decade or so that solar technologies really started dropping down the price curve, as you can see here on the right, where now we're hitting, say, down to about 4 cents a kilowatt hour or lower. Some of the best spots on Earth are down to about 2 cents a kilowatt hour of renewable electricity. So it behooves us to ask, how do we make use of that electricity, those renewable electrons, to do the chemical transformations to provide the molecules that we need across the globe? So as I mentioned, steam methane reforming is how we typically make hydrogen today. As you can see from the reaction chemistry, clearly there's quite a bit of CO2 that gets emitted. And if you say, well, what's the first experiment I could think of if I wanted to make hydrogen sustainably? And this is where you could say, well, I want to take a well-known, highly commercialized solar PV technology and couple it to a well-known commercialized water electrolyzer. So these are technologies that have been around for many, many decades. They're already scaled. We know what those cost curves look like, and they're still too expensive. So basically doing this today is absolutely more expensive than steam methane reform hydrogen. But that doesn't mean it's impossible to get down the cost curve. So that's really where the technological barriers are. How do we develop technologies? How do we develop catalysts that can be better and cheaper and can get us to that hydrogen? So to start our journey today, really diving into some of the technical aspects of this, I want to show this work from Lindsay and Jesse and Jiang. Lindsay and Jesse were former PhD students of mine. Jiang was a PhD student with Professor Jim Harris in electrical engineering. And we asked ourselves the question, yeah, how efficient can it be if you were to couple water electrolyzers with a solar photovoltaic? And so it really was an engineering design problem where you ask, well, what kind of PV, what kind of photovoltaic would I want to integrate into this system? And it turns out you might not want the best PV out there. So the best PVs, of course, generate a lot of voltage and a lot of current, but the actual curve, the voltage current curve needs to be matched to the water electrolyzers that you've designed and developed. So that's what this real exercise was about, was doing the design thinking on how to couple electrolyzers with photovoltaics and then building the electrolyzers in-house, fabricating the PV with the right properties, and joining them together. So when we did this work, as you can see on this screen, we were able to actually put 2 electrolyzers in series with this very high performance, but not a world record photovoltaic by any means, at 39%, fabricated by a local company, Solar Junction. And we were able to achieve a solar to hydrogen efficiency of 30%. So to my knowledge, this still remains of any solar to hydrogen technology, whether it's biologic or electrochemical or whatever it may be, 30%, you're thinking 30% of those incoming solar photons of that energy is getting converted into a storable molecule of hydrogen, which you could store for a minute, a week, a month, or a year. And then that really could be game-changing. So the efficiency, we're able to hit these high efficiencies, but of course efficiency isn't everything. We need to come down that cost curve, and I can promise you that this system is way too expensive to commercialize. That photovoltaic, very, very pricey. Those electrolyzers, we loaded them up with all the precious metals we could squeeze into them to give it the performance, but we were able to hit this high performance metric. Now the question is, how do we make this work well and more cheaply? And so we're not the only ones, of course, asking this question. Thankfully, there are a lot of drivers here in the EU and in the USA these days on really trying to build out more sustainable technology, including hydrogen. So in the United States, if you haven't been keeping track, really over the past couple of years, the legislation there has provided very large credits for sustainably produced hydrogen, which is really incentivizing a lot of companies to start deploying this technology at scale. So this is just a quick snapshot of a map of the different projects that we see going on in the United States. So we're talking on the order of 1 gigawatt or more that's coming down in the near term. The big question is, how many more gigawatts of water electrolyzers might we expect? Now, all of this is still happening in a region techno-economically that is not cost competitive head-to-head with SMR hydrogen. However, again, with the credits that are being offered through the government, it is incentivized heavily. So the question is, we still need to get down that cost curve to be able to compete. So what I'll be focusing on a lot today is talking about PEM water electrolyzers, proton exchange membrane water electrolyzers. And I don't want to dive too deep into the inner workings of the system, but at the end of the day, you're feeding in water and you're oxidizing it to make oxygen. The protons are stripped off of the oxygen, off of the water, pardon me, move through this cation exchange membrane and then get evolved as H2. You put electricity and water in, you get hydrogen and oxygen out. And the key thing is that this type of technology is really a very popular one, a very promising one to couple to renewables. So the question is, how do we make this system more cheaply? Well, right now, everything commercialized in this space is using platinum and iridium on your cathode and anode respectively. We got to get rid of these precious metals, not only to reduce the cost curve, but I think one lesson learned over the past several years is how delicate supply chains are and how precious resources are as well. Even things like cobalt and nickel are under pressure today based on battery technologies as well as other elements. You can imagine what a platinum and iridium might face if we were to start scaling this technology similarly. So if we wanted to dive a little bit deeper into the costs, and I don't want to go too deep into this, but really the point I want to make here is that scale gets you allows you to reduce that cost curve quite substantially. These are some numbers from the National Renewable Energy Lab that had come out with a recent analysis. And of course, when you take a real hydrogen plant like Electric Hydrogen's 100 megawatt facility, this is just a general schematic. It's more than just the electrolyzers. You have separation processes, compressors, et cetera, and you can see that as you go to higher and higher scales, you can go down the cost curve predominantly on the balance of plant, but not so much on the stack cost. And a big reason why is because of those precious metals that are in there. So getting rid of precious metals is important. And this really brings me to the role that transition metal sulfides and related catalysts can potentially play. So the two themes I want to dive into are water electrolysis for hydrogen production, green hydrogen, as well as direct solar photoelectrochemical technologies. So diving into the first of the two, water electrolysis. How do you design a non-precious metal catalyst for hydrogen evolution? We need inspiration from anywhere we can get it. And some years ago, when I was a postdoc in Denmark working together with Ib Korkendorf, there was a lot of computational work being handled by Professor Jens Nørskov and colleagues, really looking into new types of hydrogen evolution catalysts, and they found a lot of inspiration from Mother Nature. If you want to make a non-precious metal catalyst for anything, Mother Nature will probably have a good variety to look at, because Mother Nature obviously makes use of the resources that it has available to it. So if you take a look at, say, nitrogenase and hydrogenase, which are very good catalysts for hydrogen evolution, there are no precious metals in sight. Now, the computational work from Jens Nørskov indicated that these are good catalysts and explained why they're a good catalyst, and a large reason why is because of their delta G for hydrogen absorption onto those catalytic sites, which is very close to 0, and that's what you want. You want a very thermoneutral catalyst that doesn't bind that proton too tightly or too weakly in order to make that HH bond and have it come off the surface as H2. Now, that's the biological catalyst. How do you make a solid-state catalyst that you could put inside an electrolyzer and hopefully ask it to run for a decade or more? This really pointed us to the edges of molybdenum disulfide. Molybdenum disulfide is a layered material. It's a sandwich of sulfur, molybdenum, and sulfur with van der Waals forces in between those sheets. And the sulfurs on the top and the bottom, according to the calculations, should be catalytically not very good. But the undercoordinated sulfur that decorates the edge were predicted to be very good hydrogen evolution catalysts. So back when I was a postdoc working with Ib and others, we synthesized these well-defined nanotriangles and characterized them with scanning tunneling microscopy, and really showed that the activity of these molybdenum sulfide was much greater than people had thought before, and all that activity was coming from the edge. So this was a really key advance, is recognizing with transition metal sulfide catalysts, particular MOS2, the edge sites are where all the action is. And interestingly, over the past, or the previous, I should say, decade or two before this work, there had been quite a number of publications that are fantastic, beautiful surface science chemistry on molybdenum sulfide for hydrogen. They were working on single crystals, which of course don't have that many edge sites. And so it didn't look like that too good of a catalyst. But as soon as you know that the edge is where the action is, you can take that knowledge and start building other formulations. So here's Jabot and Jakob, who started building all kinds of nanowires, mesoporous materials, small molecular clusters. The long and the short of it is the more edges and the more undercoordinated sulfurs you put into your catalyst electrode, the better the performance is going to be. So here's some of the performance curves, which is a current versus a voltage. So this is current on the y-axis. The more negative you go, that means more hydrogen that you're making. On the x-axis is voltage, reference to the reversible hydrogen electrode, which means if you hold your electrode at 0 volts on that scale, you're at equilibrium. So you're making just as much hydrogen as you're oxidizing away. So your net current is 0. And the goal here is, as you tilt your voltage more negative to try to favor the reduction reaction and make H2, you want to get that current to take off as close as possible to the right, as close to 0 as you can. And you can see from these different formulations of going from 1 to 2 to 3 that we see better and better performance, because we're able to get more and more edge sites and more undercoordinated sites onto that electrode. So one of the key figures of merit that we like to use in not just our group, but around the globe, is really 10 milliamps per square centimeter of your electrode area. How much voltage do you have to put into your system to get that level of reaction rate? Now, I do want to say something about the sulfides. Because of the nature of those types of active sites, it's very different than a transition metal, which if you take a look at, say, FCC metals, the distinction between the different sites, sure, there's a difference between 100 sites and 111 sites and 211 sites and steps and corners and edges, et cetera. But in these types of materials, these more ionic materials, there's a much broader range of possibility. And so it's really important to not only know what your geometric area is, but to know what your total surface area is, which is typical of all of catalysis, as well as how many edge sites you have in this particular case. And so here, based from that previous work that I was showing, there was really a lot of fantastic work that emerged in the years after that with a lot of different performances for transition metal sulfide catalysts for hydrogen evolution. And again, the goal here is you want to get closer and closer and closer to equilibrium. So there's quite a bit of spread in the current voltage curves that you see here. And again, 10 milliamps per square centimeter geometric is our general figure of merit that we like to start with. But then the question is, what if you start normalizing to some of these other features, the electrochemically active surface area or the number of edge sites? And so interestingly, we take all that data from across the literature and then replot it, not in terms of the geometric area of the electrode, but in terms of the turnover frequency. It turns out that they all fall on a very similar set of lines, which is good news in telling you that with all these different formulations of these molybdenum sulfides, we're getting very good resiliency. A lot of different ways to make the catalyst, and it generally is pretty good as long as you make sure to put plenty of defects and undercoordinated sites into your system. But the bad news is that if you're looking for a higher turnover frequency catalyst, this is not solving that problem. We want to take these sets of curves and move them north on this axis. So for this, we're going to have to probably go to a different variety of materials. And so we started screening using calculations, again, working together with Jens Norsko and others, really screening transition metal phosphides and phosphosulfides for hydrogen evolution catalyst discovery. So here's some work from Jakob as an experimentalist working with Charlie Tsai, a PhD student who worked on the computational aspect. And what you can see with these different formulations of metal phosphides and metal sulfides, again, we can make some pretty good catalysts. And again, they fit this volcano relationship where what you're looking for is a delta G for hydrogen to be close to 0. So we're starting to really open up the toolkit of different types of materials, and we explored this further and further and further. I'm not going to dive into all the detail on the slide, except really to say that no matter how you normalize your data, geometric area, or the electrochemically active surface area, or the turnover frequency, any way you slice and dice it, we still get this volcano relationship, which tells us we have a pretty good handle on understanding what makes a good catalyst, especially if you're after non-precious metal systems. So over the years, this has really improved time and time as we look on the x-axis. As the years go on, the amount of voltage over potential that you need to put in to get your 10 milliamps per square centimeter is getting lower and lower, which is great. That means you're operating closer and closer to thermodynamic efficiency. However, there's an elephant in the room, and that is how do these catalysts function in real devices? So everything I was showing you was catalysts operating on the order of milliamps, 10 milliamps per square centimeter. The real devices actually work at 1 amp per square centimeter, or 2 amps, or 4 amps per square centimeter. So there's 2 orders of magnitude difference. And this really inspired us to say, okay, well, how do these catalysts function? So we started retooling the laboratory to start building these types of devices, real electrolyzers fabricated in a way that industry might. So we retooled the lab. And here's some of our first work coming from Desmond, where he reformulated some of these sulfides and phosphosulfides into these inks, which was not our typical electrode preparation, but was the type of process that commercial entities utilize in making these membrane electrode assemblies. So a real water electrolyzer today, a membrane electrode assembly, looks just like this. It's really 2 pieces of carbon cloth sandwiched up against that Nafion cation exchange membrane with your catalyst loaded onto it. And so what Desmond showed, here's voltage and current. Now we're flipping the axis to be more consistent with how electrolyzer community plots things. We're reaching 1 amp per square centimeter, which again is commercial grade performance, and we're benchmarking versus the iridium platinum case. And what you see is when you swap out the platinum with these non-precious metal systems, you're getting catalysts that can run at 1 amp per square centimeter, but they're still not working as well as the platinum. And that's not unexpected. To date, I have yet to see any human-made catalyst that's non-precious metal that performs as well as platinum does in acid. So there's still an opportunity for improvement there, but at least we have catalysts that can work. Now, another big question is, what about stability? And so now this really inspired us looking at this broader toolkit of sulfides and phosphosulfides and phosphides to see how they might work in a true commercial electrolyzer. So we partnered with a company, Proton Onsite, which is located in Connecticut. They've been more recently bought out by Nel, the Norwegian electrolysis company, the market leader in water electrolyzer tech. And so here 2 former researchers in the lab, Mackenzie, a PhD student, Lori, a postdoc, started scaling up some of our catalysts and shipping them over to Connecticut, where at Proton, they integrated it into their actual commercial water electrolyzer system. So here's the cobalt phosphide example where we can compare head-to-head voltage and current versus platinum. Again, not surprising, you're paying 0.2 volts extra, which you can ask, is that worth my trade-off? It's lower capital expenditure on my electrolyzer, but less efficient, so I have to spend more in electricity. You decide, depending on what your market conditions are. But the question is, will it last? And so this is an experiment that they ran at Proton On-site for 2 months continuously, and we saw absolutely no failure whatsoever in the cobalt phosphide. So at the end of a 2-month experiment where it's running at scale under a real electrolyzer condition at true output pressure, about 30 bar pressure, 50 degrees C, at 1.8 amps per square centimeter, it worked perfectly well until they flipped the switch and turned off the experiment. That was 10 to the 5 molecules of hydrogen that were produced for every 1 cobalt phosphide unit in the system. So it gives you a really good indicator that these catalysts can be both active and stable and non-precious. Now, I do want to transition here. I'm going to do a quick time check for myself to see how we're doing. Doing okay. Now I want to switch gears and say, how can we translate some of this tech into the direct solar photoelectrochemical world? So what's the idea? So you've already seen the concept on the right, which is a water electrolyzer coupled with a photovoltaic. But what if you were to take those same catalysts and integrate them directly onto the semiconductor, where you can just shine light in and make your hydrogen? So both of these options are open options. We don't have the answer as to which of these two systems is going to scale in certain ways. We know that water electrolyzers today, there's a lot of strong drivers to start building that out, but again, they do not compete head-to-head cost effectively with SMR. So we need to keep working on other options as well, and this on the option on the left is potentially feasible. The idea here is that you're lowering your CapEx of your system. If you were to directly integrate your catalyst onto your semiconductor, you shine light in anyway, you're building out your panels anyway, and then now you're just making that hydrogen, and the expense is really in collecting the hydrogen, and of course you gotta compress it and purify it, et cetera. Those are costs that we always have to contend with, but my point I wanna make here is I think both options are still ones that we need to keep an open mind on, as well as many other technological approaches to making hydrogen sustainably. Now, the key with these transition metal sulfides, coming back to really the theme of our session here, I spoke a lot to the non-precious metal aspect of it, the activity aspect of it, the stability aspect of it. There's another aspect of MOS2 which is really exciting, that is very suited to this space of direct solar photoelectrochemical hydrogen production, and that is the two-dimensional nature of the material. And so if you put platinum onto semiconductors, whether it's silicon or a 3,5 material like gallium indium phosphide, platinum is a very stable material, no question about it. But it is actually possible for the electrolyte to kind of weave its way through platinum and start corroding the semiconductors underneath. If you take a layered structure like the one that you see here, this layered structure might be more impervious to attack. So this is the question that we are asking ourselves is, can we develop an MOS2 interface with your semiconductor that is a good interface that allows electrons to flow from the semiconductor into the catalyst and then ultimately making H2, but that interface is also protective because of the two-dimensional nature of MOS2. So this is how we fabricated some of our early stage devices on silicon. You can see the dimensions are very, very narrow, only just really a couple of nanometers of MOS2 onto the silicon with underneath it, this is molybdenum metal and molybdenum oxide that didn't get fully sulfided with our fabrication method. And on the left, this is some work from Jesse, who I had mentioned earlier, who showed that when you integrate this MOS2 onto silicon, it works, and it works well. First of all, I want to note that this negative current that you're seeing here under an irradiation flux that is similar to that of AM 1.5 radiation, we're making hydrogen to the right of equilibrium. I mentioned equilibrium value for hydrogen is at 0 volts on this scale. Now, but of course we have a semiconductor underneath that's pumping up the energy of those electrons, so we're actually getting hydrogen on to the right of it, which is good news. And you can see that this is a fairly stable system. It lasted for 100 hours in this particular experiment. Not bad. Now, Lori took things further, really engineering that interface even more carefully, and was able to show, in this case, 2 months stability under continuous AM 1.5 emulated light. So again, this is a long duration experiment showing that the molybdenum sulfide is capable of lasting, even though it's only a couple of nanometers thick, it was able to last this amount of time, protect the semiconductor underneath, and provide the catalytic activity. Now, silicon is, of course, a wonderful semiconductor. We use that quite a bit in the photovoltaics industry. But the problem with silicon is that the band gap is too narrow to provide sufficient voltage for unassisted water splitting. So you can always tile up your photovoltaics and come up with other kind of engineering approaches there. But what we think would be maybe best cost effectively is if you can develop a high performance PV that provides you approximately 2 volts of open circuit voltage, you should be able to split water in an unassisted way. And so this is where we worked with NREL to team up on achieving exactly that. So NREL is one of the top fabrication facilities across the globe at making high-performance photovoltaics, especially 3.5s. And so we worked with Todd and James and others at NREL who sent us these very high-performance tandem 3.5 systems. We coated them with the same type of design with the molybdenum sulfide catalyst. And what we showed here on the data on the bottom right, this is work from Ruben and Mija, 2 former PhD students in the group, that if you put platinum ruthenium on this catalyst, which is their champion catalyst, it only lasts an hour or 2 before catastrophic failure. But with the MOS2, as you can see, it lasted about 10 times longer. Now, it only lasted about 12 hours, which doesn't sound too exciting. There's much that we need to figure out on how to get this further, and we have. Now we're well beyond 100 hours durability in our lab at the moment. But this was actually an important achievement because once you have something that can last 11 or 12 hours, it means you can put it out into the real daylight. And so under real world conditions, that's a very different set of durability criteria than when you're under a very gentle, so to speak, lab environment with AM 1.5 simulated light. So NREL has a really nice facility on their rooftop called a solar radiation laboratory where they can make measurements for PVs or for photoelectrochemical hydrogen production, where you're tracking not only the performance of your system, you're tracking the solar irradiance moment to moment, the humidity, the wind, everything. And so we wanted to understand from a diurnal perspective how the system would last. And again, now that we're north of 10 hours, we can start to ask and answer those questions under real world conditions. So you can see we were able to make that measurement. It was about 12% efficient, solar to hydrogen, unassisted. There was no external bias. And there's a lot of data here that we can unpack. But the point is we're actually capturing things like when clouds pass overhead or when temperatures change. This was a day in January where we made these particular measurements. And in Colorado, January is pretty cold. So these are functioning, but they're not lasting as long as we had hoped. And that really inspires us to say, well, how do we make things more durable? We know that if we want these technologies to be cost effective, they have to last a decade or more. And this just gives you a sense of where we are on the roadmap, we being society working in any solar to hydrogen photoelectrochemical approach with any catalyst or any semiconductors. The US Department of Energy has determined that this is where the target needs to be based on the techno-economics, which is roughly 25% efficient solar to hydrogen and making approximately 10 to the 5 milliliters of hydrogen per square centimeter over the course of its lifetime. And when you take all these data points, these are data points of unassisted water splitting systems that are above 1% solar to hydrogen, and you can see that on an efficiency point of view, we're not close, and on a durability point of view, we're not close. But the truth of the matter is that we're much closer in efficiency than we are in durability. This is a linear scale, this is a log scale, so you can see we're orders of magnitude away from the durability target, but we are actually at least within an order of magnitude of the efficiency target. So durability is becoming a major factor that we're really diving into in this last segment of my talk. I just want to kind of dive into this question of can molybdenum sulfide, recognizing the theme of the session. It's metal sulfides, it's sulfide catalyst, it's circularity, it's sustainability. Can MOS2 provide sufficient durability for solar PEC applications? So the approaches I was showing you earlier of running experiments, making photoelectrodes, putting them under different conditions and seeing, determining their lifetime before failure is certainly one very important approach. We're trying to understand things more in detail mechanistically. And so especially when it comes to diurnal cycling, which we think is going to be a major challenge in this field. It's very different than a water electrolyzer typically, where you can just run that thing 24/7 at full tilt. And so we know that the solar irradiance curve looks something like this, and thanks to Kyra and Swati and Adam, we've really been developing protocols to understand diurnal cycles or on-off cycles or some type of combination of those. And ultimately, we think these irradiation profiles can be simulated by different potential profiles that we're applying to our semiconductor catalyst electrode interface. The tool that we're bringing to bear to understand this more mechanistically is inductively coupled plasma mass spectrometry. This has been an absolutely wonderful advance in the technology itself, and then coupling it to catalytic chemistries, especially in the electrochemical world, where dissolution is a common degradation mechanism. And so really leveraging fantastic work from others, we've developed our own methodologies using ICP-MS, coupling them to these types of electrode systems, and that's the data that I want to show you today. Very fresh data we've been getting over recent weeks. So speaking of data, there's a lot on this slide, and what we're doing here to simulate MOS2 on silicon, so we grow it very similarly to the way that I was showing you earlier on our photoelectrodes, and now what we're doing is we're just driving things not with daylight, but with just a potential. And so we're pretty much trying to reproduce what voltage sequences look like if this thing were under the sun, when the sun goes down at night, when it comes back up in the morning. And so we're doing these cycles, and it's on the order of tens of thousands of seconds, so really it's many, many hours of experimentation. What we're doing is as we're driving the voltage, we're measuring the hydrogen evolution current that's coming off of it, so it is an active catalyst, and we know that, and we expect that. And all the meanwhile, this data on the bottom in blue, this is our ICP-MS data. And what this is showing is that when we're cycling between the volts of positive 0.15 volts versus that reversible hydrogen electrode, or negative 0.55 volts, okay, these are generally where you'd expect operation to be, we see very little degradation. It's hard to read this axis. This is approximately on the order of tenths of a picogram per square centimeter per second. Okay, so we have very good detection capability with the ICP-MS that is online to detect degradation products. And so under this drive cycle, the molybdenum sulfide is looking very stable. What happens under true diurnal situations when you actually reach, when it's nighttime? And the sun goes over the horizon, and now you're at open circuit voltage. The open circuit voltages will go all the way up to positive 0.5 volts versus the reversible hydrogen electrode. And as you can see, the ICP map just tracks that very consistently, where that's when our catalyst is degrading. So in other words, when you're under operating conditions, it looks very stable under these reducing conditions. As soon as you go to open circuit voltage, that's when bad things really start to happen. So then we ask the question, well, recognizing that, from a fundamental degradation point of view, how would you design your electrode to last better? And this is where we designed a drive cycle where we're still at, say, negative 0.55 volts versus RHE, which is kind of noon and June conditions when the sun is the strongest and you're driving the most hydrogen. And we limited it so that it never went higher in voltage than it needed to maintain a very, very light current of only 50 microamps in the electrochemical cell. And so the goal here is that by maintaining just a very, very light cathodic current, negative current, we can try to maintain some cathodic protection on that molybdenum sulfide, and indeed, we're right back down to the same type of degradation rates that we saw before. So this is really all pointing to strategy, saying if you want this thing to last for a decade or more under true on-sun conditions, different materials are going to have different degradation processes under the diurnal cycling. We're already learning what we need to do with MOS2 to protect it so that it can last rather than tens of hours or hundreds of hours and under true on-sun conditions, hopefully on the order of tens of thousands of hours. So with that, I want to go ahead and wrap up and see if there are any questions. The goal here, of course, with this theme of today's session, again, I appreciate so much the invitation to be here today. It's all about sulfide catalysts, circularity, sustainability, and I hope I've convinced you that there is a role to play for these types of catalysts and these types of technologies. We still have a long way to go, no question about it, but there's a lot more promise than ever, especially when we're looking to reduce our use of precious metals. So with that, I want to thank my team, thank funding sources predominantly from DOE that funded this work. Thank you for your attention, and I'd be happy to take any questions.